Hello students and welcome to a new lecture about the quantum numbers. We did discuss in the previous lecture that we had to come with the quantum mechanics so we can explain the multi-electrons atoms and the emission line spectrum that didn't agree with the simple hydrogen atom model. So Schrödinger is the scientist who came up with the wave function that solved that problem and allowed us to understand the electronic structure of different atoms. So solving the equation or the Schrödinger function led to 4 quantum numbers. The first one we are going to cover is the principal quantum number n. So the quantum numbers, the 4 of them, will describe the distribution of electrons in an atom. And the principal shell are orbitals of approximately the same size and energy. So the principal quantum number for any given electron, if 2 electrons are sharing the n, it means that these 2 electrons have similar size and energy when it comes to the orbitals they occupy. N has values, and the values of n start with 1, 2, 3, and so on. Again, n is called the principal quantum number. The higher the n, the higher the energy, because the electron will be further away from the nucleus. So the higher the n is also telling us that the size of the orbital is large and further away from the nucleus. And number of orbitals in any given n can be calculated by n to the power 2. Generally speaking, n describes the distance of electron away from the nucleus. The smaller the n, the smaller the distance away, or the closer the electron is to the nucleus, and the larger the n, the further away it is. Here is an example. All these are s orbitals. The only difference between them that they occupy different n levels. So this here, the first one, this 1s, this is an s orbital that is located at n equals 1. This is an s orbital located at n equals 2. That's why we call it 2s. And the last one is an s orbital located at n equals 3, and that's why we call it 3s. So the number at the beginning is describing what is the principal quantum number. And if you look at this picture, the nucleus is the same. It's the same atom. But if an electron is in this orbital, it's very close to the nucleus. This is further away from the nucleus, and this is even further away from the nucleus. When it comes to every shell or principal shell, there are subshells within that shell, and that's the quantum number L. So it is what we call the angular momentum quantum number L, and the subshell is part of the principal shell. Orbitals in that subshell have same energy and similar shape. Generally speaking, when some orbital has the same n and L, we are talking about the same orbital when it comes to distance and when it comes to shape. Number of subshells are equal n. What does that mean? When it comes to n equals 1, we only have one type of subshells. When it comes to n equals 2, we will have 2 types of subshells, and so on. Generally speaking, what you need to know that the angular momentum quantum number L does describe the shape of the orbital. L takes values, and the values of L starts from 0, 1, 2, 3, all the way to n minus 1. So when L equals 0, this is in reference to an orbital that we call S. When the value of L is 1, that's the orbital we call P. When L equals 2, that is the orbital that we call D. And when L equals 3, that's the orbital we call F. So L has different values. Every value corresponds to a certain orbital with a certain shape, because remember, L thus describe the shape of the orbital. When L equals 0, that's S, and S is a sphere. And when it's 1, it's a P, which is 2 lobes, and so on. Now, when it comes to the energy, and please let me just explain this here. So, energy increase with increasing the L value, which means S orbital is the lowest energy, then P is higher energy than S, D is higher energy than P, and F is higher energy than D, as long as they all are on the same principal quantum number or the same N level. Here is L equals 0, which is S orbital. When we say 1s, it means that this specific S happens to be at N equals 1. The second one is 2s, which means N equals 2. They all have the same shape because S means quantum number, angular quantum number, L equals 0. So they are all S. The difference between them is the N number, which makes one of them smaller because it's closer to the nucleus, and like F3s, for example, is much larger, and electrons in it will be further away from the nucleus. When L equals 1, this is the P orbital, and if you look at the P orbital, it's made of 2 lobes. These 2 lobes can either align themselves in one of 3 ways, either on the z-axis, the x-axis, or the y-axis. So therefore, I'm going to have 3 of them. One of them is going to be called PZ, one of them is PX, and the other one is PY. When L equals 2, we are talking about d orbital, and d orbital is definitely more complicated when it was mathematical calculation to come up with their shapes. There are 5 of them depending on the axis that they are located. You don't need to know the differences in those axes. You just need to know that there are 5 of them. The next quantum number will be ML, and ML specifies the different number of a certain L, meaning we call it the magnetic quantum number ML, and what it describes is the orientation of the orbital in the space. I just showed you when it comes to P, you have 3 orientation. So, orbitals with electrons with the same values of N, L, and ML. So if any electrons share the same value of N and L and ML with another electron, it means that they are in the same orbital. ML takes value starting from negative L, passing 0 all the way to positive L. Each subshell has a specific number of orbitals, can be calculated by 2L plus 1. Now, remember that when it comes to S, I have only 1 ML value because sphere have only 1 orientation. When it comes to P, I'm going to have 3 ML values because I have PX, PY, and PZ. And when it comes to D, I'm going to have 5 different orientation. And when it comes to F, I'm going to have 7 different orientation, and so on. So here are the 3 different P orbitals. We have PX, PY, and PZ. What does that mean? One of them will have a value of ML equals negative 1. The other one ML equals 0, and the last one ML equals 1. Where does that come from? Remember, ML take a value from negative L, passing 0 all the way to positive L. When it comes to a P orbital, L equals 1. So therefore, ML values will be negative 1, 0, and 1. Each one of them represents a separate orbital. Every ML value represents a separate orbital. So ML negative, that will be corresponding to any one of them. It doesn't have to be PX. It can be PY, PZ. But there are 3 of them because I have PX, PY, and PZ. When it comes to for D, L equals 2. So the values will start negative 2, -1, 0, 1, and 2. 5 different values. I have 5 different orientation in the space. Last quantum number is what we call ms, which we call the spin quantum number, because electrons, think about it, in an orbital, they will either be spinning like a clockwise or counterclockwise. So there are only two values, either ms equal plus 1/2 or -1/2. And that depends on how they interact with a magnetic field. We find out it depends on how they spin. If they spin clockwise, then they are going to be differentiated than the electron that spins counterclockwise. Again, there is no association with direction and value. All you need to know that one of them will be plus 1/2, the other one is -1/2. That also in support of that the maximum amount of electrons in any given orbital will be 2 times the orbital, because any orbital can only hold 2 electrons. One has to spin clockwise, the other one has to spin counterclockwise. The maximum number of electrons in a shell will be equal to 2n squared. Now let's look at all this. I really hate those equations that, encourage memorization. You actually can understand it by looking at this table together. When n equals 1, because remember, when n equals 1, L is 0 all the way to n minus 1. So n minus 1, 1 minus 1 is 0. So we only have one value of L, which correspond to the 1s orbital. The possible values of ml, which is -L passing 0 all the way to L, will only be 1, 0. So I have one value, which is 0. Therefore, the number of orbitals, because ml values are number of orbitals. 0 is one value, which means I have one orbital. So the total orbitals in that n equals 1 will be 1 orbital. Now let's look at, in a different color, I want to look at when n equals 2, I'm going to have two L values. I'm going to have 0 and 1. 0 correspond to 2s and 1 correspond to 2b. When it comes to ml value for s, it's only one value, which is 0, one orientation for the sphere. When it comes to ml, 3 values, because I have px, py, pz. So one orbital that comes from S and 3 orbitals that come from P. So at n equals 2, I have a total of 4 orbitals. Now let's look at n equals 3, and we're going to do a different color. When n equals 3, I have 3 L values, because remember, it's 0 all the way to n minus 1, which is 3 minus 1, 2. So 0, 1, and 2. 0 is 3s, 1 is 3p, and 2 is 3d. For 3s, I only have one orientation, so one orbital. For p, I'm going to have 3 orientations, 3 orbitals. And for d, I'm going to have 5 values, which means 5 orientations and 5 orbitals. So when you count number of orbitals for that level, it will be 9 when n equals 3 again. Now let's look at 4. When n equals 4, I have the 0 value for L, the 1, the 2, and the 3, because it's 4 minus 1 all the way up to 3. That means 4s, 4p, 4d, and 4f. S1 orientation, P3 orientations, D5 orientations, F7 orientation. You add up all these orbitals together, and you're going to end up with 16 orbitals when n equals 4. Now, if I told you here what is the max electrons you can fill, then for n, you have one orbital for n1, so you can put 2 max. For n2, you have 2 orbitals, so that's 4 max. Every orbital can hold up to 2. for n equals 2, you have 4 orbitals, so that's 8 electrons max. For n equals 3, you have 9 orbitals, so that will be 9 times 2. That will be 18 electrons max. And when it comes to 16 for 4, that will be 32 electrons max. Now let's solve the following. How many 2p orbitals are there in an atom? Number of orbitals are depending on ml value. What is ml value for 2p? Well, ml depends on L. It goes from negative L passing 0 all the way to L. For P, what is L? Remember, for P, L equals 1. So ml values will be negative 1, 0, and 1. 3 values means I have 3 orbitals. The px, the py, and the pz. How many electrons can be placed in 3D subshells? If I want to know how many electrons I can place, I need to know how many orbitals. How many orbitals? It's the ml value. For D, L is 2, so ml is negative 2, negative 1, 0, 1, and 2. Now, if I want to address that, it means I have 5 orbitals. Every orbital can host up to 2 electrons, so the total number of electrons should be 10 electrons. Given the values of the quantum numbers, give the values of the quantum numbers associated with the orbitals in a 3p. So what are the quantum numbers? I have n, l, ml, and ms. Okay. So for n, it's a 3. For L, P, remember, S is 0, P is 1, D is 2, F equals 3 when it comes to L value. So this is a P, which means 1. For ML, the values can be anywhere negative 1, 0, or 1. And for MS, I either have plus 1/2 or negative 1/2. These are the possible values. What is the total number of orbitals associated with the principal quantum n? Okay, when n equals 4, right, L values will go from 0 all the way to n minus 1. So that means that L values will be 0, 1, 2, and 3. Now, orbitals come from ml values. For 0, I only have one ml value, which is 0. For 1, I have negative 1, 0, and 1. For 2, negative 2, negative 1, 0, 1, and 2. And for 3, negative 3, negative 2, negative 1, 0, 1, 2, 3. So now if you add them up together, this is one orbital, these are 3, these are 5, these are 7, right? So now if you do the math, you're going to have 7 plus 5, 12, 12 plus 3, 15, plus 1, 16. You have 16 orbitals, right? Because you have 4s, 4p, 4d, and 4f. This one has 1 orbital, 3 orbitals, 5 orbitals, and 7 orbitals. Okay, now we are going to end this lecture here, and the next lecture we will talk about electron configuration.